Okay, thanks very much for the pair of introductions here, and it's definitely a privilege to get to speak in this lecture series. I'll also just to check that people can see from the back that the thing is scaled to avoid the little pixels that are out here. So see much in between there. If you're in the back, can you see the words that are there? That's big enough. Okay, but let me know if you run into an issue with that. Great. So it's again, it's a pleasure to be here. I'll talk about some actually. So I'll say that Ellie and I were discussing this morning that I first met Ellie in 1993 when, as an undergrad, I was at the PODC conference presenting some joint work with someone who at the time was another Cornell undergrad, Senthil Mullainathan. And over the next 15 years, Senthil and I kind of went our separate ways. I went into computer science. He went into behavioral economics, became an economics professor at Harvard, working in this behavioral space, thinking about the intersection of human behavior and public policy issues. And sometime around 2011, we got in touch with each other because Senthil was noticing that although our professional interests had kind of been diverging since we had been undergrads, they were starting to actually come back into alignment because somehow my interest in algorithms making decisions in society and his interest in humans making decisions and their societal implications were starting to converge as we saw an increasing number of domains where human decision makers and human domain experts were beginning to rely on tools from AI, tools from machine learning to make what we think of as these sort of high stakes decisions. And so there was something at this intersection that seemed interesting to think about. And so around 2011, we started thinking about some of those questions at the intersection of human decision making and algorithmic decision making. And that's led to some of the work that I'll talk about here. In the end, we've been joined in this effort by a number of collaborators. The work I'll talk about is with a particular collaborator here, my current PhD student, Manish Raghavan. So to try setting up, why we thought there was this intersection between Senthil's interest in human behavior, my interest in algorithms. Let me start with something that algorithms are quite good at solving, which is making recommendations. All right, so this is a screenshot of a help screen from the Netflix homepage, and it's giving a little explanation of how it goes about making recommendations. And as you all know, it takes your viewing history, and it takes how you rated different movies, and it looks at how other people rated different movies and what number of stars they gave to them. And it makes a prediction. Like it predicts that for this movie, it guesses that you're going to give it 4.3 stars, for example. Right? That's the guess it's making. Right? So effectively, it's taking you, who have some very complex set of tastes and interests. It's reducing those complex tastes and interests to a feature vector. It's passing it through an algorithm trained on a lot of people's feature vectors, and it's estimating a probability. What is the probability that you're going to like this movie? And in some sense, the starting point for what I'm going to talk about is this observation that there are a lot of processes that go on in the human world, not assisted by technology, that have some of this flavor. Hiring sort of has this flavor. If you're applying for a job, you construct a resume. It gives your past education, your past work experience, and you submit it to a hiring committee. And that hiring committee can't evaluate you, the real person. It evaluates this set of features derived from you that are encoded on the resume, right? Not unlike how the Netflix algorithm has no access to you, the person. It has access to a feature vector. And based on that, they are estimating something. Actually, what they're trying to estimate is completely unclear, right? What is a hiring committee trying to figure out? Are they trying to estimate whether you'll succeed at the job? Are they trying to estimate whether you look like their other employees? Are they trying to estimate whether you'll work well as a team with the other people? We'll come back to that. Part of the challenge here, of course, is once we leave the algorithmic side of the, Netflix at least can say exactly what it's doing. A human hiring committee has a much harder time saying what it's actually trying to do, but it's doing something. We could say the same thing with college admissions, right? If you're a 12th grader and you go to apply to college, the college admissions committee doesn't have access to the real you. It has access to your application, which is some tabular representation of you, on which they're again trying to estimate something, although they would be hard pressed to say exactly what it is that they're trying to estimate. Right? All three of these are cases that follow a sort of similar template, right? Engagement with online content, um, hiring committees, admissions committees, all of them sort of follow this pipeline in which we have an individual, they get reduced to a set of features, pass through an algorithm which is estimating the probability, that you'll like the movie, that you'll be a good employee, that you'll succeed in college. And we often create taxonomies of these things, right? So the things like hiring or college admissions are often referred to as high stakes decisions because individually, each of those matters a lot to somebody's life, right? It matters a lot to this person if they get a job, this particular job, or if they get into this particular college, in a way that, it ultimately is not that important whether Netflix was correct about whether you're going to like this movie. Now, high stakes and low stakes is a little complicated here because we have certainly seen over the past few years that you take, low stakes decisions like which news article to show you online or which of your friends' comments to show you. We take 100 billion of those and can add up to something extremely high stakes, like the formation of public opinion in an entire country. But every one of those decisions is very small, whereas each of these hiring decisions or admission decisions individually can be quite significant. Okay, so for all these reasons, because these things are starting to individual decisions materially affecting people's lives, being made by humans, sometimes being assisted by algorithms, right? Increasingly, hiring committees may use data science resources. Admissions committees may use data science resources. We started asking questions about what are the societal impacts of these decisions that we're making. And in this area, we can ask a number of questions, right? We can look over here on the right-hand side and say, to the extent that we're using an algorithm to estimate these things, are we focusing on the right objective function? We can look on the left-hand side. We can ask, is our mapping from individuals to features the right mapping? Could we do that better? Could we be collecting other features of people? And third, we could be asking, are the algorithm's decisions fair? Right? Is the algorithm engaging in fair decision-making? Is it somehow perpetuating bias? And of course, I put the word fair in italics here because much of the talk will actually be spent trying to figure out what we might mean by this word fair. Right? It should certainly not be apparent at the outset what we mean by that. So, Sendel and I were thinking about these kinds of questions. And we were actually trying to understand the effect of algorithmic tools to estimate probabilities, to estimate risk, in a number of domains. And in summer of 2016, which is where I'll sort of start the more detailed part of the story, we encountered an issue in a domain that, in a sense, is even more high stakes, where there's even more individually high stakes decision making, where we had been looking at some of the use of these algorithmic tools and trying to assess their impact. And that's in criminal justice. Okay. So if I think about criminal justice as a domain, this is an area where we're starting to see the use of algorithmic and data science tools, and for the following reason. It has to do with the nature of the law around pretrial detention. So if someone is arrested for a crime, and here I'll talk about U.S. criminal law as it's applied in state criminal law in the U.S., they appear before a judge who has to decide whether they're going to wait for trial out in the community or in jail. And having someone wait for, and this is essentially what we think of informally as the problem of assigning bail, although it's a question really about pretrial risk more than about specifics of bail. Now, we'd very much like to avoid the situation where someone waits for trial in jail. That's an incredibly destructive act, right? It could cause people to lose their jobs, to lose custody of their children. We would like to have people wait out in the community. The law instructs judges to say you should let someone await trial out in the community, provided that you predict that they will return for their court appearance without committing a crime. So if you look at the law, unlike elsewhere in the pipeline of criminal justice decisions, pretrial detention asks the judge to make a prediction. And so many jurisdictions around the country have said, if the law is asking this human judge to make a prediction based on this person's past criminal history, past engagement with the legal system, and if we know that algorithms trained on data are very good at making predictions, isn't there some way we could let algorithms help out? And the question is, does the assistance of an algorithm, which is potentially very good at making predictions, help or hurt in the kind of societal goals that we have for this pretrial detention system? Okay, so one example of such a tool is this tool called Compass, which you can think of as following exactly this pipeline. An individual, a defendant appears in court. there's some record of their past criminal history. That's the feature vector that we're using. The algorithm then creates a probability of risk. Right? Is this person likely to reoffend? Are they likely to not appear for their court appearance when the trial is held? And so, if you're a defendant, what you don't want is a high score from the school. Right? A high score is what gives a judge license to detain you. Okay, so we were thinking about tools like this, what effect they have on judicial decision making, what effect they have on the overall system. And in summer 2016, the investigative journalism group ProPublica put out this report that was very widely circulated, which announced machine bias in this very large font size. And what they had discovered, they had basically gone and collected a lot of data in which this particular tool, Compass, which was made by a commercial vendor, it was not the one that we were actually, one of the ones that we were actually looking at. They collected a lot of data on how it was being used in Broward County, Florida. And this was in the kind of modern style of data journalism, where they actually created a GitHub repository for the article they had written. It had the data they used, they had the code they used to analyze it, and a lot of people, including us, took the data, looked at it, and tried to figure out, what were the claims that they were making. Now, a number of the sort of pieces of their methodology got critiqued, and justifiably so. There were certain decisions they could have made differently. But no matter how you went and looked at their data and reproduced what they were talking about, certain facts were robust. Certain facts were simply the case in this data, no matter how you chose to exactly do the analysis. And here's a sort of kind of pair of these facts. They're closely related. What they found was that let's stratify defendants by race, and let's look at African American defendants and white defendants who did not subsequently go on to reoffend. Right? So these are people who, whether they were detained before trial or not, they were released on the community eventually, and we looked at whether they had gone on to commit a crime. Right? So these are people, no matter what the risk tool thought it was doing or thought it was assigning its probabilities, ultimately these are people who did not do anything wrong after they were. And what they found is that African American defendants who didn't subsequently reoffend had higher average scores than white defendants who didn't subsequently reoffend. And this is somehow in and of itself a problem, because we're talking in this first bullet point about a whole bunch of people who didn't go on to do anything wrong. And one group had higher average scores than the other group. They were basically bearing a higher cost of the inaccurate predictions. And there's a corresponding fact in the second bullet. White defendants who did subsequently reoffend had lower average scores. All right, so lots of discussion around what this meant in the summer of 2016. And again, despite a number of critiques of the methodology, no one disagreed that this was present. So what to make of this? Well, the first set of responses came from people who work in criminal justice policy, actually along with the people behind this tool. And they pointed out that actually there's a different way of looking at what was in that data, and a different property that tool had been designed to satisfy. This is not directly an answer to those two bullet points. It's simply something else you ought to know about the tool and how it was designed. It was designed to obey a property called calibration. And here's how calibration works. So let's think about, again, these scores, think of them as probabilities that someone's going to reoffend if you release them, right? They're a measure of risk. And again, if you're a defendant, you do not want to be given a high risk. Let's imagine these scores are discretized. So rather than think about, the actual real number, think about it as I create these bins. That one's labeled 0.1, that one's labeled 0.2, and so forth. And I put defendants into one of these bins according to the discretized level of risk that they have. Okay. Now, a property that the Compass tool had is if I took all the defendants who got a score of S, and I look at that group, an S fraction of them go on to reoffend. Right? So everyone who's labeled 0.1, 10% of them went on to reoffend. Everyone labeled 0.2, 20% of them went on to reoffend. And that was true separately in each racial group in the data. I looked at all the African American defendants with a score of S, and S fraction went on to reoffend. All the white defendants with a score of S, and S fraction went on to reoffend. Okay. So the argument that the people sort of arguing for the calibration definition made, and the people behind the tool, is that S means S. A score of S means if I look at everyone afterwards, an S fraction then went on to reoffend. That was all it was ever intended to mean, and it meant that independent of race. You could add race as a variable, and it would not change that estimate. Okay. And it does seem like if you're going to have a risk tool and it's going to output a score of S, it should at least satisfy this property. It should be the case that, when I say this group of people has a 20% chance of reoffending, 20%. That might be clear, although let me try arguing that, let me just add one extra bit of weight to this argument, because we're going to ultimately have to sort of make some decisions among all of this. Imagine that we did not have calibration, right? Because we can imagine, well, maybe even if the scores weren't calibrated, we just all agree to use them as these scores, and we won't worry about the factor calibration. But you quickly run into problems, right? What is the problem with using a rule that's not separately calibrated by group? And to motivate this, let me talk about not criminal justice, but a sort of metaphorical story or a sort of cartoon story about hiring. Let's imagine I'm hiring doctors, and I have a risk tool that gives probabilities that this person will be a good doctor if I hire them. So in this example, high scores are good, because I would like someone who has a high probability of being a good doctor if I hire them. Okay? And so maybe what I'll do is I'll use these scores, and I'm going to hire everybody in the highest bin. They're the best candidates. Now, imagine I'm using a rule that is not calibrated with respect to gender. So, right, I'm going to hire people with scores in this highest bin over there on the right. And suppose that female doctors with this highest score of S star are actually more likely to be good doctors than male doctors with the same score of S star. Right? That's what a failure of calibration would mean. Two groups, but F star doesn't mean the same. Well, then the point is, if that were really true, then as a patient, it would actually be rational to choose your doctor, at least in part, based on their gender. Why? Because the rule is telling you to do that. The rule is saying S star doesn't actually mean the same thing for the two genders. If you see a score of S star, it's actually more likely to be a good doctor if the person is female. Okay? And so this is the kind of problem that you run into if you have a failure of calibration. Okay? Whether or not hiring committees agree to use the rule as specified, you're rarely the final consumer of your own decision. And so downstream, people like patients might actually choose doctors using sort of this feature. Okay, so we'd like to have calibration. And the compass rule was calibrated. But ProPublica's objections about the compass rule remain, right? This differential average scores, right? Calibration is good. We have it. We don't have these averages. And so we asked the question, couldn't we achieve all these desired properties at once? So Sendel and I were looking at this, and around this point we were joined by my PhD student, Manish Raghavan, who had just arrived in grad school and was interested in these questions. And so we thought to ourselves, let's try to figure out what's going on. Because by the time we were really asking this question, the ProPublica report had been out for a couple months. And there was just really an enormous amount of discussion in the community about what to make of all of this. And we somehow felt like we're talking about relatively specific, well-defined measures on this data set. If we could simply figure out exactly what's going on, maybe we could understand what all of this controversy is about. And so it really was a case of trying to just write down all the definitions, because we sort of hoped that would make things clear. And in the end, it actually sort of did. So let's write down the definitions. And I think from what I've said, it doesn't take much of a leap to write this sort of more carefully. In a formal model, I have individuals. There's sort of two important things about the individual. They either are a positive or negative instance, right? They're either going to go on to commit a crime or they're not, right? Positive or negative. And we're interested in disparities across two groups. Let's call those two groups A and B. Individuals come from either group A or B, right? For example, A or B could correspond to, different groups according to race, according to gender, some protected attributes like that. And they're either positive. And then this risk tool is going to assign, there's going to be some feature vector. It's going to assign a score to them. Again, the scores will be discretized. So I can think of classifying the individuals into these bins. And bin B will have some score V sub B, which is supposed to function like a probability of risk. Okay, so I think that says everything here. So bin B, the number attached to it, just is sort of supposed to be a stand-in for a probability. Now, what are the properties we've been discussing so far? Well, so far there have been three of them. One is calibration within groups. For each group, a V sub B fraction of the people in bin B are in the positive class. Okay? So that is to say, I look at the bin labeled 0.2, I look at all the white defendants who are put there, and 20% of them should go on to reoffend. That's calibration. And then we have the 2 points that ProPublica talked about, which I'll call balance, because we'd like to balance the averages. So balance for the positive class So the average score of the positive members in group A should equal the average score of the positive members in group B. Right? And that was their point about people who went on, who didn't, went on to reoffend had different average scores in the two groups, which was in and of itself a problem. And similarly balanced for the negative class. Right? The people who didn't go on to reoffend should also have the same average score across groups. The average score of negative members in group A equals the average score of negative members. All right, 3 definitions. And the real question was, it's sort of a problem of designing an algorithm that takes people's feature vectors, produces risk scores, and satisfies these 3 properties. Right? We have a specification. We just like something that meets that. So what do you do in these kind of situations? Well, one thing you can do is sort of think about, we'd like to achieve these 3 properties with some kind of algorithm. Sometimes you start with the simplest cases you can think of. Right? Let's start with something very simple where we can solve it. And if we can find something very simple where we can solve it, and then we can kind of grow outward to a slightly more complex cases, then we'll see, can we eventually solve the general problem. All right, so let's think about special cases. Here are 2 special cases where I claim I can satisfy all 3 of these properties. Calibration, balance for the positive class, balance for the negative class. All right. One is what you could call perfect prediction. Something you're unlikely to encounter in real life, but again, we're looking for simple special cases. Let's imagine that, the feature set has the property that it's so expressive that you can actually deterministically tell if someone is in the positive class or the negative class. And that for every value of the feature vectors, the probability is either 0 or 1. Well, then I can actually satisfy all 3 properties. I simply assign a 0 to everyone who I know to be in the negative class, a 1 to everybody who I know to be in the positive class, and you can verify that I've satisfied all the properties. Again, not something we're likely to encounter. Second, the case of equal base rates. Suppose groups A and B had the property that they have the same fraction of positive instances. Right? So in each group, 30% are positive instances and 70% are negative. And I can certainly create a risk tool that has the 3 properties. You won't find it a particularly interesting risk tool, but I could create one giant bin, put everybody in it, and label it 0.3. It certainly is calibrated in both groups, and everybody has the same average. So I've satisfied all the properties. Again, not a particularly useful one, but now we have these sort of 2 extreme points where we now have actually satisfied all the properties. And the question that Sendel, Manish, and I asked ourselves was, can we start to kind of grow outward from there and find more interesting cases? And we tried that for a while, and then that plan came to an abrupt end with the following theorem that we were able to prove, in which Alex Chultikova at Carnegie Mellon proved a version of this around the same time, that in any instance of risk score assignment where all 3 properties can be achieved, you must have either perfect prediction or equal base rates. These are, in fact, the only 2 cases where you can satisfy all 3 of these properties. In other words, ProPublica found something, wrong with what the risk tool was doing. People observed that the risk tool was calibrated, which is a good thing that you would like to have. And the point is, all 3 of these things could not be satisfied simultaneously by any risk tool in general, right? Any risk tool that people deployed is going to be susceptible to one of these objections. Some notes here. When you see a theorem containing a negative result for designing an algorithm, it's always good to ask, where is this coming from? Because obviously, the field of computer science is full of negative results that we would like to prove and seem very hard to prove. This is not one of those. This is actually not a theorem that's about limited computational power. I could give an algorithm all the computational power I wanted, it would not be able to satisfy all 3. It's also not a theorem about limited data or inferential power. Right? Even with lots of data, you could not do this. It's really a much more basic thing. It's really about trying to get a whole bunch of averages to all come out equal, and arguing that that's not going to be possible. As a result, because it's not about computational limits or data limits, it really applies to any decision procedure. It's not really about algorithms, although it was discovered because people were using an algorithm. But whatever it was that Broward County was doing before it started using the Compass risk tool had some version of the same problem. Because it's a problem about any way of assigning risk scores to people. Okay? And so, fundamentally, it's saying you have to choose, right? There are a bunch of reasonable definitions here that we would like to satisfy. You can't satisfy them all. It's now not a technical question, right? We can't derive for you which of these you would like to satisfy. That's a question that society has to reach some resolution. I want to show you just a couple slides about how the proof works. Because, again, as promised, once you sort of figure out what all the definitions are, understanding why this theorem is true is not actually, in the end, that complicated. But before I do that, so just to mention some other work that was happening in parallel around the same time. Actually, at the end of 2016, ProPublica kind of surveyed all the activity it had generated with its report in the summer and produced a second report. Not sure whether that's the headline I would have given it, but it sort of surveyed these things, including a number of other interesting lines of work. For example, this nice work of Hart, Price, and Trebro, which has gone on to generate a number of follow-up results as well, looking at if we give up on calibration, how well can we do if we want to equalize the average for the negative class and the average for the positive class. And I'll single that one out there. So how to prove this thing? Okay, so a sketch of the proof in 2 slides, which actually is pretty much a complete proof. Okay, so again, we have these groups. Let's index them by t. So I have, let's say n sub t is my total number of people in group t. And let's say k sub t is the expected number of people in the positive class in group t. Right? These have nothing to do with my risk tool. These are just facts about the world. Now, the calibration condition, well, if I think about the bin over there on the left, it's labeled 0.1. So 10 people get a score of 0.1. Also, which is a total, I hand out a total score of 1 to that bin. Similarly, one person in that bin actually is positive. The next bin, I hand out 0.2 to 10 people. So the total score I hand out in that bin is 2. And 2 people go on to re-offend or positive. So more generally, the calibration condition, what it's really telling us is that the total score of all the group T people in bin B is equal to the expected number of people in the positive class. Total score I hand out is equal to the expected number. And I add that up over all bins, and it's basically saying the total score I hand out to group T is equal to the expected number of people in the positive class. All right. Slide 2 of 2 in proving this thing. So n sub t, number of people in group T, k sub t is the number of people in the positive class, which we've just concluded, thanks to calibration, is also the total score handed out to the positive class. All right. 2 other numbers I need. These do come from the risk tool. Right? Let's say x is the average score assigned by the risk tool to someone in the negative class. Let's say y is the average score assigned by the risk tool to negative class to the positive class. Now note, that's not xt and yt. That's x and y, because it's independent of the group. The groups have to get the same average. That's key. Okay, so let's look at this thing here. My laser pointer vanishes silently into the screen. So the total score in group T. On the right-hand side, one way of writing it is just, thanks to calibration, it's k sub t. The other way is on the left-hand side. There are kt people who are positive, and they get an average score y. And there are nt minus kt people who are negative, and they get an average score of x. That's also a way of writing it. So that gives me a linear equation in the 2 unknowns, x and y. And I get one of those equations for each of the 2 groups, A and B. So I have 2 equations in x and y, 2 unknowns, and let's plot them in the xy plane across the 2 groups. Now, no matter what I do, those 2 lines are going to intersect at the point 0, 1. If they don't have the same slope, that's all, they only place they intersect. If they do have the same slope, they'll intersect along a whole line. Okay, now let's unpack what that means. The point where they intersect, 0, 1, is perfect prediction. I give 0 to all the negatives, 1 to all the positives. And if they have the same slope, that's equal base rate. Then they can intersect anywhere they want. Okay. So in some sense, the theorem, which said I can only do this in the case of perfect prediction or equal base rates, like, it was not an absolute negative statement. It didn't say I could never do it. It said I can only do it in these 2 cases. And that condition, perfect prediction or equal base rates, was sort of like a 0-dimensional condition, a point, perfect prediction, glued to a line for equal base rates. And somehow, in the end, the proof actually has that point glued to that line. And that's where the negative is. Okay. So again, a case where once you sort of finally get all the definitions right, it's ultimately sort of clear what's going on. But the deeper point really is that somehow there's a choice to be made. These are all reasonable definitions. And which one you want is going to depend on society's objective, the domain you're working in, a number of things, but we're not going to derive it from some all-encompassing formal framework. So we thought about this, and then we, from here, moved on to a number of other questions. And I wanted to talk about one of these. So far, everything I've talked about has really been about evaluating individuals. Right? We audited the outcome by summing across a whole number of individuals, but the decision was made about the individual. On the other hand, there are lots of cases where the decision I'm making is really about a set, right? And at the very beginning, when I was motivating things with the example of hiring or the example of college admissions, I was attempting to argue that even the objective function that you might have is not obvious when you're doing college admissions, right? What is it you're actually trying to do when you do college admissions? And at the very least, it's clear you're not thinking about the individuals you're admitting. You're thinking about the class you're admitting. We all sort of intuitively know that because we read headlines like this one from about a year ago now in our local newspaper, the Cornell Chronicle. The accepted class of 2023 is the most diverse ever. Now, it sort of goes without saying that no one individual is the most diverse ever, right? That's a statement about a set of people. And it's something that you might well, in admissions committees do, want to optimize for, right? But it's a property of the set. And this idea that sometimes when we optimize for measures like diversity, we're actually optimizing a set function was really sort of brought to the fore in the quantitative social sciences by the work of Scott Page at the University of Michigan, who did a lot of very interesting work, starting in the early 2000s, at the sort of performance-enhancing effects of having diverse groups. And think about that as an optimization problem, right? Arguing that even from a purely self-interested point of view, you should favor diversity, right? Independent of all the other benefits that diversity brings, it even brings simply performance. Okay. And there are a lot of cases where we think about this. So one question is, as we start thinking about these kind of quantitative interventions, what role do they play in these kind of diversity measures? Well, the first question to ask would be, what are the obstacles to achieving the full level of diversity that we might otherwise have? And one certainly that's been extensively documented is implicit bias. Right? Implicit bias in selections that we make. So again, I'll think about selection where we have these distinguished groups, and we may be concerned about bias against particular groups. A long line of work in psychology and behavioral science, behavioral economics, on documenting the ways in which there's sort of these systematic biases when people go to evaluate individuals. In the mid-1990s, there was a lot of interesting quantitative data that people began to collect. So one of the classics of this literature is by two social scientists from Sweden, Christine Veneros and Agnes Bold, who got under sort of some version of a freedom of information process the reviews for European research grant proposals. And one of the questions there was to take the PI and assign them some kind of a competence score based on their past track record of research. And these two researchers who were auditing this data tried to come up with lots of possible measures of impact, number of publications in top venues, total citations to those publications, many, many different ways of doing it. And more or less, however they did it, they found some version of the fact that's shown in this plot here, which is that for a fixed value of past scholarly impact, women applying for these grants were getting lower scores on this measure than men applying for these grants. This was simply a systematic effect all the way across the impact spectrum. Now, this led to a number of follow-up pieces of work because, of course, in the end, each of these people is a different person. And, maybe there are confounds. Maybe people work in different areas. Maybe those areas have different levels of citation patterns and so forth. And so there were a number of attempts to kind of deal with those confounds. The sort of strongest of which perhaps was one of the first papers by my co-author, Sendel Mulanathan, shortly after grad school, working with Marianne Bertrand, who did what has become one of the most replicated studies in the social sciences of the past 20 years. What they did was they took fictitious resumes and they sent them to prospective employers. And to half the employers, they put names that the employers would think of as, as they put it statistically, would make them think of these people as being white applicants. And the other half, they put names, again, drawing data from from the U.S. Census about common first names for white and African American people in the U.S. who would cause people statistically to think of them as African American applicants. And the callback rates for the people who employers would presumably think of as African American applicants were about 2/3 what they were for the white applicants. And you would like to, you would hope that maybe that gap has gone down over the years, but this is a study that gets reproduced, on a very regular basis, and that gap persists, right? These are identical resumes. Literally, the only thing different is the name at the top. And so in the spirit of randomized control trials, this is somehow telling us something very strong about the persistence of bias, purely based on that. Okay, so we have these issues with bias standing in the way of us, actually essentially hiring the right people. What do we do about this? So there's an intervention that people have looked at, and it works as follows. And I'll describe it in a sort of relatively stylized form, right? We're imagining that we have a large pool of applicants. We'd like to choose a short list of K of them. Say we'd like to interview these K people. We'd like to hire them. We'd like to give them an award. We'd like to give them a grant, something. Okay. And the concern is that perhaps the construction of these short lists is biased against one of the groups. So the two groups, we'll call them X and Y, and we're concerned about bias against the X candidates. What to do? Well, so one intervention that has become increasingly popular is this thing called the Rooney Rule. The Rooney Rule is named after Dan Rooney, who was the owner of the Pittsburgh Steelers in the year 2002. And the owners in the NFL in 2002, faced with the profound lack of diversity in head coaching positions, the fact that there were very, very few head coaches at the time in the National Football League who were from minority groups. Faced with that, and admittedly faced with an impending class action lawsuit about that, they got together and they asked, how could we police ourselves, make up a policy that we would all voluntarily agree to take part in that might do something about this? And so what they decided was that every time we go to interview for a head coaching position, at least one of the people we interview will be a minority applicant, will be from an underrepresented group. So the start in the NFL, it began expanding out. It gets used in a number of domains, including academia. If you've been on some sort of a hiring or selection committee, you may well have discussed some version of using the Rooney Rule, even if you didn't call it by that name. It was proposed in 2015 by then President Obama to the tech industry that they should use this for executive hiring. And legal analysis of it has argued that it actually sort of threads this interesting path in that it's something which is effective and also, seems to not be challengeable legally. So, effective. This is actually, retrospectively, in 2016, Cynthia Dubois looked at the effect of the first 15 years of the Rooney Rule in the National Football League. And it's actually, these are very small numbers. I mean, in the end, right, this is not a large data analysis. There are only so many teams in the NFL, and they each have one head coach. But right at the introduction of the Rooney Rule, you saw a jump in the number of head coaches from underrepresented groups in a way that you did not see for other positions not affected by the Rooney Rule, offensive and defensive coordinators, NCAA Division I. So it seemed to have some effect over time. But we were curious, looking at this, about a sort of purely static question, which is, what is the effect on the quality of candidates in a one-shot sense? I'll try to formalize what I mean here. But effectively, this is sort of aimed at the part of the discussion about the Rooney Rule that goes as follows, right? People, when they're sort of asked to use the Rooney Rule, express the concern that without it, you're engaging in unconstrained optimization. You're allowed to pick any set of K people that you want. Whereas with the Rooney Rule, you're engaging in constrained optimization. You're only allowed to pick sets that include at least one member of Group X. And as we all know, unconstrained optimization must win because it's optimizing over a bigger set. You just have more choices. And we thought to ourselves, is it possible that that's not actually that simple? That maybe that argument, which sounds very compelling, there might be something wrong with it, right? What could possibly be wrong with it? Well, because we know that the human beings engaged in this decision-making are making mistakes, right, because of their bias. They're not actually necessarily choosing the best people, right? That's what this plot back here is effectively telling us. And so if I have someone who's making mistakes, sometimes constraining their behavior can actually lead to an improvement, right? Any of you who have ever, taught or taken a class that has homework assignments has seen certainly some version of this, because I certainly have had the experience that you go teach a class and you plan to assign, say, 6 homework assignments. And here I'm just talking about in another case where people engage in behavioral biases through procrastination. You have 6 homework assignments. One thing you could do is say, you're all grown-ups here. Here are all 6 homework assignments at the very start of the term. I want you to pace yourselves and make sure they're all handed in by the end of the term. And as anyone who's ever done this knows, that turns into a complete disaster. Because people with the best of intentions don't pace themselves, and they sort of wait, and they end up trying to do everything at the very end, and then you have to end up doing some intervention because it doesn't work. So what do? Instead, even though you know what 6 you want to assign, you have the first one due in week 2, the next one due in week 4, week 6, and so forth. You have constrained their behavior. And in the process, you've helped them. And you think to yourself, how could that be? Doesn't unconstrained optimization beat constrained optimization? I've constrained their behavior, and I've gotten them to perform better. But that makes sense when you're dealing with agents who are making systematic mistakes. Right? By constraining their behavior, you're cutting out the part of the space on which they are making those mistakes. Could it be that something like this is happening with the Rooney Rule? That the Rooney Rule is a constraint on people's biased behavior in a way that might improve their performance. So we thought about this, and we thought, could we write down a model that somehow captures that intuition, that maybe this is a constraint that's actually helping? What would a model for selection look like? It would need to include 3 things at minimum. It would need to include a notion of a distribution of quality for the candidates that you're looking at. It would need to include the fact that X and Y are each different fractions of the pool, right? The relative abundance of X versus Y. And it would need to include some measure of the bias that's keeping you from making accurate decisions. Okay, so here's a quick gloss on how we might create those 3 ingredients, and then I'll tell you what it was that we found. So first of all, each candidate has a numerical potential for future performance. And I want this model to be as simple as possible because we're going to discover even it's pretty complicated. But at least we're going to sort of turn all the dials to as simple as possible. So imagine that we don't have an inference problem. We actually see, but for bias, we would see these values exactly. And I'm just trying to hire the best candidates, the ones with the highest measure, the highest numbers among Z1, Z2, and so forth. Where do these numbers come from? Well, the Rooney Rule is typically applied in what you might call creative professions. I'm trying to hire faculty with high numbers of lifetime citation counts. I'm trying to sign music artists who will have large numbers of downloads. I'm trying to sign YouTubers who will have large numbers of views. In all of these areas, citation counts, download counts, view counts, revenue generated, these all tend to follow what are called heavy-tailed distributions, in which large values are unusually common. So let's take a very simple heavy-tailed distribution, because again, I want everything to be as simple as possible. Let's say that each zi is coming from a power law distribution. The probability that zi exceeds t is some t to the minus 1 plus delta. As delta goes to 0, very large values become increasingly common. Right? So this is basically, I'm in a domain dominated by superstars. I look at the top person, it's like, I want to hire this person because they are a superstar. They're just way out there in the distribution. And as delta goes to 0, that's more and more. Okay. The objective is just I want to choose k candidates to maximize the sum of their zi values. Now, I'm also going to assume that the decision maker can't actually directly access these numbers. They can just make ordinal comparisons. They can look at 2 people and say, I think this one is better than that. All right. I need relative abundance of groups, and I need bias, and then I can state a result. Relative abundance of groups. Okay, so I have n candidates from group Y. Let's say I have alpha n from group X. Now, X was the minority group. So therefore you can imagine alpha is less than 1 if you want, but alpha really could be anything. And the values that all these candidates have all come from the same power law distribution. And because I'm not assuming there's any inference problem, I actually see these numbers, right? So it's as though I look at job applicants, say for a faculty position, and for some reason, and I don't recommend this if you're hiring a faculty position, I care just about their lifetime citation count. And I see their citation counts perfectly. I'm just trying to pick the top K. I have a sorting problem. The only problem I have is that I experience bias. And the bias is the third parameter. I have delta, the power law exponent. I have alpha, the abundance. I have this bias beta. When I see a Y candidate, I evaluate them perfectly. I see YI. But when I see an X candidate, I evaluate them with bias. I don't see XI. I see XI divided by beta. Right? They're scaled down. Now, if I could manipulate these numbers perfectly, I could correct for that if I want to. But again, I can only make ordinal comparisons between these numbers. So I just think this one looks better than that one. But do I think that because the numbers are really in that order, or because the bias on the X candidate has pulled them down and the comparison has inverted? That's the question. Okay, so we have drawn from power law alpha and X candidates and Y candidates. The X candidates are shrunk down by this factor of 1 over beta, and I sort them and I take the top k. And I can either just take the pure top k with my bias, or someone could come and impose the Rooney Rule on me and make me choose one of them from group X. And now we see, at least, there's a question. Being forced to choose from group X could hurt me, because I'm now engaging in constrained optimization. I can't necessarily choose the set I was going to choose. But it could be helping me, because the reason I'm not picking that person from group X might be because the bias pulled them down, and this is forcing me to take them anyway, which might actually be in my interest, since my goal was to maximize the sum of these values. And so Manish and I looked at this, and the basic result here is that I'm in this space given by these 3 parameters, right? Delta the power law exponent, alpha the abundance, and beta the level of bias. And that space actually gets carved up into 2 regions. One in which the Rooney Rule is helping and improves performance, and one in which it's not helping, it's not improving performance. And what we can do is actually characterize how the space gets divided up. We can characterize the decision boundary in terms of those 3 terms, for which the Rooney Rule either helps or hurts. And the trade-off turns out to actually happen at values for which all of these things, right? All 3 of these values were designed to be things that are in principle measurable. I can certainly measure alpha. I can measure the composition of the pool. Enormous amounts of empirical work have gone into trying to estimate the best fit power law exponent for things like citation count. So we have some knowledge of that. And the level of bias, again, studies like the Benner-Ross and Volt study, beta is certainly the one where there's been the least work, trying to estimate that difference. And so that's the result. For each size of the shortlist, the characterization of the boundary in the space between where the Rooney Rule helps versus hurts, and in particular, a non-trivial portion of the space where it's actually helping. Right? I'm constraining your behavior, and yet I'm helping you perform better, even on the objective function that you believe you're trying to solve. We'll say a couple things. That's even just for k equals 2, the boundary is somewhat complicated. I write this down just to not to decrypt it, but this is actually alpha, beta, delta space. This is the actual decision surface for 2 candidates. It has some strange non-monotonicities in it that we don't fully understand, right? So even this model that we try to make as simple as possible has some complicated behavior. The one point I want to talk about before wrapping up, and I'll conclude, is this cliff at the end where it diverges up to infinity. Because it's certainly the case that if I'm only hiring 2 people, and alpha is very small, right? There are a very small number of X candidates, and I'm simply trying to maximize performance, it may be the case that reserving 1 slot is too much for preserving, right? It's a very, very small fraction of the population, and I'm only trying to reserve, I only have 2 slots, right? Reserving 1 comes at some cost, even in a world with very, very large bias. But it's surprising. So let's ask that question. Let's ask the question where that surface diverges up to infinity, which basically says, for which pairs of alpha and delta does the Rooney Rule improve utility in the world of infinite bias? Because it turns out by asking that special case, at least for me, I ended up learning something about the nature of bias and discrimination that I really can't say I had fully understood until writing down this model. Okay? So let me run through this one slide here to kind of put my finger on one concrete thing, sort of novel thing that I feel like I actually learned about bias for having worked through this. Okay, so infinite bias, not a world that we, fortunately, that we live in, but in a world of infinite bias with 2 slots, if you don't use the Rooney Rule, you're just going to pick the top 2 Y candidates. If you do use the Rooney Rule, you'll pick the top Y candidate and the top X candidate. Again, because we're in a world where you're able to perceive perfectly without except for bias. Okay, which one should you do? Right, and again, alpha is the relative abundance of X candidates, delta is the power law. Here's a surprising fact, which is, no matter how small the fraction of X candidates, no matter how small alpha is, there is a small enough power law exponent so that the Rooney Rule actually improves utility and expectation. So that you should actually use it. Right? 2 slots. The question is, do you reserve 1 for X candidates? No matter how small the fraction of X candidates, right, X candidates in the population, there is still a small enough power law exponent, right, a strong enough heavy tail that you should actually reserve one of those two slots, no matter how small a fraction of the population. So this seems surprising. There's some math you can work out to argue that. But let me instead argue more intuitively. And let me actually start with the fact that when we first proved this fact, we spent a few days saying this can't possibly be true. And I'll tell you why it didn't seem like it could possibly be true. I mean, it's certainly counterintuitive. But more than that, let's imagine a world where 20% of the applicants are from group X, 80% are from group Y. And you're telling me I should reserve one slot for somebody from group X, even though they're only 20%. Now, let's take group Y, and let's divide them into two sets A and B, arbitrarily. Okay? They're all group Y, but one's A, one's B. Now, the best person in group A, in expectation, is better than the best person in group X. Why? Because it's twice as big a group. They're all from the same distribution. Similarly, the best person in group B is better than the best person in group A, also because they're twice as big a group. So I've just named for you two people from group Y who, in expectation, are better than the best person in group X. Yet you're telling me that given two slots, you should reserve one for group X. How can that possibly be? But it turns out that this argument is wrong. It's what's wrong. And the theorem is actually right. And the reason is, we're not talking about picking one of A or B and not the other. We're talking about picking the best person from A or B. And the question is really, do you want the second best person from group Y or the best person from group X? And the amazing thing about heavy-tailed distributions, such as we encounter when we work in professions that include things like publication citation counts or download counts or revenue generated, is that with heavy-tailed distributions, the max is so much higher than the second max. That the max over 20% of the population is likely to be better in expectation than the second max over 80% of the population. And that ultimately is somehow the true cost of bias in this situation. Right? By engaging in bias, by sort of disregarding this 20% of the population from your decision-making, you're ultimately excluding somebody who in expectation is actually better than this second best person that you chose from this group. Right? And that's actually what you're giving up. And that's effectively what the Rooney Rule is forcing you to correct. So that's sort of some intuition for how this kind of constrained optimization that the Rooney Rule, an intervention that people are increasingly using, might actually be improving performance, even in an absolute sense, even independent of the benefits it might have for other aspects of increasing diversity. There are a lot of other interesting directions here. I should wrap up in 1-2 minutes. So let me just say a whole bunch of other things implicit in this model. We've made certain choices. We chose things that came from a power law. We chose bias that was multiplicative. We chose a noise-free model. The Rooney Rule asks you to reserve one slot, but you could ask, what is the optimal number of slots to reserve in a model like this? You could potentially derive that. And finally, I mentioned we were asking a static question. There's a lot of interesting work dating back actually to the work of Ken Arrow in the 1970s on the dynamics of discrimination, which points out certain pernicious dynamic aspects that the discrimination has, independent of its static form. For example, and this is sort of Ken Arrow's point, which is continued on into work in the economics and recently the computer science literature. If you're in a group that's experiencing discrimination, and you ask yourself, should I invest costly effort in acquiring stronger credentials? Then if you're in the group that's experiencing discrimination, that effort that gives you this credential is effectively being taxed by the fact that credential is less valuable because it's going to be evaluated by people who are discriminating. And in a world where your effort is being taxed and someone else's isn't, it's rational for you to spend less effort, right? Because some of it's being lost to discrimination. What does that mean? It means if you're in the group experiencing discrimination, you're going to put less costly effort into acquiring credentials. You'll have fewer credentials. And the person's bias, the person's discrimination, has somehow come true because you, in fact, have fewer credentials at the time when you go to apply for jobs. Right? And so a discriminatory belief can actually become self-fulfilling because the people experiencing discrimination don't invest the effort to go and acquire that. And so that's the kind of cycle that you can potentially break if you're introducing interventions that are forcing people to actually correct for the biases that they otherwise are either unwilling or unable to correct. And so with that, I'll wrap up. Again, part of the issue here is that there are many possible definitions of what it means to achieve fairness, to eliminate bias. And as we saw in the early parts of the talk, you can't actually satisfy all of these simultaneously. There are more reasonable definitions than you might be able to satisfy. And secondly, that by constraining people's behavior, you can actually sometimes achieve better outcomes because with the bias, their behavior was leading to suboptimal outcomes. So relatively complex behaviors, relatively simple interventions, I think this is an area where this sort of mathematical modeling activity has proved surprisingly useful at helping contribute to some of the debates about interventions and policies. Ultimately, the question about what are the societal objectives that we're trying to achieve is something that all of society has to engage in. But I think increasingly it's something where ideas from computer science and mathematics has a role to play at contributing to that conversation going forward. Thanks very much.
Any questions? So if you're sitting in the front, actually, you can use the microphone directly. If you're sitting behind, I will pass the microphone to you.
Okay. I remember a story from diversity training that in hiring people for a musical performance.
Yep. Yeah. 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 No, I think that's an interesting. It's a very interesting point. And the example of auditioning behind a screen is something which comes up a lot as the case where the criterion that you're evaluating on can almost be completely separated from these other features you might be perceiving. I mean, I think the argument is that in a lot of the domains where, so I think we should be looking for more of those opportunities. Absolutely. I think there are a lot of domains, and particularly the ones where some of these interventions in hiring, such as the Rooney Rule, are being talked about, where the applicants that we're considering are sort of known, through their past track record. And so it becomes, as you said, it's hard to do it in faculty hiring. It's hard to do it in many professions where there's some long track record that's sort of part of the evaluation. But I think not enough thought has been given to the question of where can I separate the signal on which I'm optimizing from the features that I'm trying to avoid having contributed to the bias. And it's entirely believable that there could be some potential computational interventions that might actually help with that. Yeah. Okay. Yeah. Yeah. That's why I think that there's a lot of interesting work that's going on right now in these issues of when there's bias in the data upstream, what are the options available to me for correcting for it? And so one kind of argument that comes up there is that the this is sort of a counterpoint in the design space is that the protected attributes that we often want to withhold from the human decision maker because we don't believe they're going to use them correctly. Maybe things that we want to give to an algorithm that's trying to correct for the upstream bias, right? That the bias is already there. And so a canonical example is, for a human admissions committee, we may say, I don't want knowledge of the applicant's socioeconomic status to figure in your admissions decision. You shouldn't be basing it on that. Because you may end up using that as a proxy, for things, and I would prefer you just evaluate them on the record. On the other hand, let's think about, two college applicants. One has a 1300 on their SATs, and they went to some, extremely, highly resourced K through 12 education, in a school district where they had lots of SAT prep, they had lots of background. The second person has a 1280 on their SATs, and they went to an under-resourced K through 12 school system. They had effectively no preparation, and they got a 1280. Now, if I look at this, I might say, my goal was not to admit the people with the highest SAT score. My goal was to admit people with the highest capacity to succeed in college. And the SAT score is simply a noisy signal of a latent variable. Now, if I were trying to estimate that latent variable from this noisy signal, and my choices were the 1300 from the person who had endless prep and the 1280 from someone who had very little prep, I might actually think the 1280 is actually more predictive. Right? We'd have to decide what. And so, in order to correct for that, you might want to give an algorithm knowledge of their socioeconomic status so as to invert that signal. The very same thing I might want to withhold from a human committee if I didn't trust them to use it correctly. So I think part of the question really is going to be these kinds of variables, sort of how do we believe they might be used by algorithms, how do we believe they might be used by humans. The answer this is not to say that that's going to be a cure-all, or that that's even necessarily going to work. It's simply arguing that the question is complicated as to sort of when I use these features and when I don't use these features. But I think these are exactly the sort of kinds of questions that use of these data analytic tools are sort of at least helping us out. Yeah, it's a good question. I mean, I think part of the question really is this gets at different formalizations of what it would mean to achieve some level of equity between two groups that have different distributions of, say, resources. Right, and so I have two groups, different distributions of resources. I want to now produce outcomes for them that represent some level of equity. And so this notion of the thought experiment in which someone from group X, imagines running group Y, and vice versa, is certainly one style of reasoning that people engage in. But I think all of it is sort of a question about sort of what are reasonable formalisms of these things. I mean, again, I think one sort of point in all of this is that one sort of potential, not necessarily anticipated benefit of starting to use algorithmic tools in some of these domains is it's forcing us to be much more specific about some of the questions that we're asking. Right? If I think about, say, the process of hiring, it's very, very hard for human beings to actually say, here is the objective function that we're optimizing. When anyone who has ever hired somebody, if you were to say, can you write down all the way to sort of first principles what it is you're looking for? I mean, it's very, very hard for human beings to do that. Even when human beings, in good faith, attempt to give you a description of their criteria, it's very hard to tell whether they're actually following it, even if they're intending to follow it. And so one thing about using algorithms in this pipeline, right, independent of are they helping or hurting, which is something we should debate, they're certainly forcing a certain level of explicitness in the objectives that's causing us to have these kinds of conversations. And it's causing us to ask these questions, which I think ultimately is going to be valuable even simply for the policy discourse that surrounds all of this. Thanks.